Okay, so we're going to continue graphing just a few more rational functions. This is about the third video on graphing rational functions. So hopefully you've seen the first few before this one. So let's get into it. So here's a function that I want to graph. And as usual, we'll start with our x-intercepts. And possibly, okay, we've been talking about even and odd functions, and if you can spot a function as even and odd, it can sometimes help while you're graphing it. This one's especially, I guess, probable that it might be even because I only have x squareds in both the numerator and the denominator. So let's check for even and odd, but I already started the x-intercept, so let's go ahead and follow through with that. So if we set this equal to 0, x-intercepts are going to come from the top being equal to 0, and we should factor that completely if we want to look for the idea of the intercept going through or bouncing off the x-axis. So here I can see I have x-intercepts of 1 and -1, and in fact they're coming from odd powers. That's why you want to factor it so you don't get tricked into thinking it comes from an even power. So both of these intercepts will pass through. Okay. Yeah, since we brought up odd and even, let's go ahead and check for that and confirm that what we think is that it might be an even function. And sure enough, if you replace both of those x's with negative x's, you can see that that's not going to change, and neither is this one. So it's just going to become the exact same function that we started with. That up, which means this is, so f of negative x is the same as f of positive x, so we know this is an even function, so it's going to have symmetry about the y-axis. Okay, go back to intercepts. Our x-intercepts are 1 and -1. Let's put those in right here, -1, +1. Since it's not, one of my x-intercepts is not 0, I can have a y-intercept for sure. I'll just put that right here. Y-intercept, if you let x be 0, this is just going to be 1/4. Maybe about right there. Okay. And then the next thing I would usually check for is a vertical asymptote, which comes from where f of x is undefined. And in this case, I would be looking for where x² + 4 is equal to 0. But notice there is no answer to this, right? This says x² equals -4, which has no real solution. So maybe that's why I put this one on this video. It's just a little bit different. There doesn't have to be a vertical asymptote on a rational function here. There is none in this case. So there are none. Okay. We could still possibly have a horizontal asymptote, however, which we know comes from setting the limit, finding out what happens to this function as x goes to infinity or -infinity. So okay, so this is going to give me some kind of infinity over infinity. Although maybe you can kind of tell here, if x went to +infinity, 1 minus +infinity squared, that's going to make this actually -infinity. And if I plug in actually either one, plus or minus infinity, this is going to be infinity on the bottom. So you can tell I should be getting a negative answer. And we discussed on a previous video that the shortcut for doing these horizontal asymptotes is to just focus on the terms that have the highest degree on the top and the bottom, which is just -x² over +x², which cancels out, and I end up with -1, which as expected is negative. So I have a horizontal asymptote, I use HA for that, of y equals -1. Back to our graph up here. Okay, so I know that as x goes to infinity, it has to approach y equals -1. It also has to go hit these intercepts and go through, so it pretty much makes sense that it should be approaching from the top, go through this intercept to my y-intercept. And now, knowing that this is an even function, if this is what the left side looks like, then we know the right side should look identical if you reflected this about the y-axis. So it has that symmetry that we usually see with an even function. Okay, so no vertical asymptote on that one. So that one's a little bit different than some of the other ones we've done. Okay, let's look at this next one. Now this one's unusual, and I'm going to go ahead and tell you why. This particular function has two horizontal asymptotes. All of the ones we've done so far, it's been the same horizontal asymptote, whether x goes to positive infinity or negative infinity. But here we're told that there's two of them, so that's going to be a little bit different. So we'll get to that. Let's start, as usual, with our intercepts. If I set my function equal to 0 for my x-intercepts, only way that could happen is if 0 is equal to the square root of x squared plus 1. If I square both sides, that means 0 would have to equal x squared plus 1. And notice that gives us something similar we saw in the last problem, where you have to take the square root of a negative number. There's no solution to this, right? So what does that tell us? That must mean there are no x-intercepts. I don't think we've seen that before. And that's okay. That just means our graph never touches the x-axis, right? That's actually good information to know that it never, ever touches this x-axis. Now, I do have a y-intercept. If I let x be 0, it's just going to come down to the square root of 4 over 1, which is 2 over 1. So my y-intercept is 0, 2. Right there. My vertical asymptote, which comes from where my function's undefined, which would be when x plus 1 equals 0. And that's going to be negative 1. Now remember, with vertical asymptotes, we classify them as either same or opposite, having to do with what power this negative 1 came from. And you could argue that this came from a factor that's to a power of just 1. So this is what we would classify as opposite. So let's put that in our graph. So negative 1 right here. So if on one side of the asymptote, the graph goes up, the other side goes down, or vice versa. That's what we mean by opposite. Okay, now we get into the horizontal asymptotes. Since we've got some indication that there's actually two of them, what that kind of suggests then, to find our horizontal asymptotes, where we normally have been considering the limit as x goes to plus or minus infinity together, we should probably separate these out into looking at as the limit as x goes to positive infinity, and then the limit as x goes to negative infinity. Right? It must mean that we're getting two different answers here, that if there's supposed to be two of them. And in fact, I just want you to see how you can tell there has to be two different horizontal asymptotes, because if I plug in positive infinity here, square it, add 4, take the square root, my numerator is going to be positive infinity, and my denominator is going to be positive infinity. And a positive over a positive, I should definitely get some kind of a positive answer. But if you look at this one, if x goes to negative infinity and I square it, that's back to positive infinity. Plus 4, take the square root, my numerator goes to positive infinity. But if I put in a negative big number into the denominator and add 1, this is going to be a negative number. And a positive over a negative is going to be a negative. So you can see, unless the answer is 0, I should be getting a positive asymptote in one direction and a negative asymptote in another direction. As we've said, we can just focus on the highest power of x in the numerator and denominator. So I'm just really focusing on the square root of x squared and x. And the square root of x squared, most people would say, is just x over x, and that gives me 1. And that's correct. So there's a horizontal asymptote of y equals 1 as x goes to positive infinity. Now here, it would seem like you're going to get the same answer. Because if I focus on the highest power, it would seem like you're just going to get x over x again, like we did here. But there's actually, you're not going to, and here's why. I kind of just went really fast through this and said most people would say the square root of x squared is x. Well, that's not always true. Okay, let's think about this. If I have the square root of 3 squared, yeah, 3 squared is 9, square root of 9 is 3. So that certainly fits the idea that the square root of x squared could equal x, right? It's just whatever you're squaring. But what would happen if I did the square root of negative 3 squared? If we believe the square root of x squared is equal to x, then it kind of would force me to say that the answer is negative 3, right? But clearly it's not. If I square negative 3, I get 9, and the square root of 9 should actually be positive 3. So I can get the correct answer if I then apply another negative. Now I get the correct answer of positive 3. So the way it works is the square root of x squared will just equal x, but what's the difference here? As long as your x is a positive number, if x is positive. But if x is negative, we see that the square root of x squared is actually equal to the negative of x, the opposite of x. It's like a piecewise function. Okay, that's kind of a tricky idea. So how do I know? Well, if x is going to negative infinity, then I know that this is negative, huh? This tells me that my x, when I plug it in there, that it's going to be a negative x. So the square root of x squared, this is actually negative x over x. And negative x over x is negative 1. And so then we see we get a horizontal asymptote of y equals negative 1 in the negative direction. So let's look at this on our graph. In the positive direction, I'm just going to say 1 here, we get a horizontal asymptote of 1. But in the negative direction, it's negative 1. So it would look like this. You don't have to draw them all the way through because we know that it's only approaching 1 in this direction and it's only approaching negative 1 in the negative direction. So there's no reason to draw it all the way through. Now for the graph, well, we know it has to go through this point. So that would seem to indicate that it should be coming from up here. It's approaching positive infinity as it gets close to our vertical asymptote and approaching 1 in this direction. Remember that this was an opposite vertical asymptote. So if we're pretty sure that on the right side, the graph goes up, on the other side, the graph is going down and approaching y equals negative 1 in this direction. And notice that also what gives us more believability that our graph is right, there are no x-intercepts, huh? Nowhere did my graph cross the x-axis. Okay, last couple here. Okay, so this one here, this one I want to use to perhaps correct some misunderstanding, particularly about how to find vertical asymptotes, right? I've been saying all along, you find vertical asymptotes where f of x is undefined. Well, that's kind of true and kind of not true. I need to be really clear with this example, because clearly this function is not defined when x is 5, right? F of x is undefined because I'm going to get 0 in the denominator at x equals 5. So that means it's not in my domain, right? My domain does not include 5. However, there's a difference in this one. If we take our function and factor the top, it ends up factoring into x plus 3 times x minus 5. And we can see that not only would 5 make the denominator equal to 0, but it would make the numerator equal to 0, right? These are going to cancel out. And so it would appear then, it would appear then that there's no more vertical asymptote. And what is my graph looking like? It looks like just the graph of f of x equals x plus 3. Now you might say, well, wait, why can't I plug in 5 now, right? Because if the x minus 5s cancel out, why can't I plug in 5? Well, when we decide on the domain of a function, we have to decide on it before we do any canceling. If I were to plug in 5 at the very beginning, I would get 0 in the denominator, which means that's not part of my domain. So the graph will look like x plus y equals x plus 3, but it is true that x cannot be equal to 5. The graph of y equals x plus 3 is just a line with a y-intercept of 3. Let's just call this 0, 3, and a slope of 1, up 1 over 1. It's going to look something like this, with one exception. To show that the graph is undefined at 5, so let's say this is 5 right here, there's not going to be a vertical asymptote, there's just going to be a hole in the graph. And it's going to look, just continue on, it's going to look just like the graph of y equals x plus 3 with a hole. Here we go. Graph looks like, just like y equals x plus 3 with a hole at x equals 5. So to be totally clear now, right? How will we tell when we have a vertical asymptote for a rational function? You want to make sure you factor the top and the bottom. If you get a common factor and it cancels out, that's not going to be a vertical asymptote. It's going to actually be a hole in your graph. Now, if nothing were to cancel out the x minus 5, then it would be true. I would have a vertical asymptote at 5. Okay. So we want to keep that in mind. Let's do one more. So what you'd probably want to do now from here on out is make sure you factor everything completely before you do too much work on it. So here, if I take out a 5x, I'm going to be left with x plus 2. X squared minus 4 factors into x minus 2 times x plus 2. And you see the common factor of x plus 2 that's going to cancel out. So what is that telling us? We're going to have a hole at x equals negative 2. Since the x minus 2 did not cancel out, that means we are going to have a vertical asymptote at x equals positive 2. And then everything else is the same, and you can really just graph what's left over. After those cancel out, we're left with 5x over x minus 2. We just have to remember there's going to be a hole at negative 2. So your x-intercept, okay, and we know that comes from setting the top equal to 0. That's going to be 0. Comes from an odd power, so that's going to be a through. We already got our vertical asymptote, our horizontal asymptote. If we take the limit as x goes to plus or minus infinity, that's going to be essentially focusing on the highest power on the top and the bottom. That's just 5x over x, which is going to give us 5. So we have a horizontal asymptote of y equals 5. Let's say this is y equals 5. Vertical asymptote of x equals 2. We know we had an intercept of 0. That was a through intercept. So if you think about it, if it's got to approach this asymptote in this direction, it kind of has to come through this way, doesn't it? It wouldn't go this way because it wouldn't get close to 5. So, but what did I forget? When x is negative 2, we know there's a hole in the graph. So right about, here, we just want to indicate that there's a hole there. This was, I didn't talk about it, but this vertical asymptote of x equals 2 comes from an odd power, so this would be an opposite. That's why I knew if this side went down, here we go, if this side goes down, then the other side must go up. If you do want to know where this hole is, you could just plug in negative 2. If you plug that into, so let's talk about this hole here. If I plug in negative 2 to what's left over, I end up with -10 over -4, which is 10/4 or 5/2. So this hole actually has a coordinate -2, 5/2. Which makes sense, that's below 5. All right, so I think we've covered pretty much everything on graphing rational functions, including some strange examples on this one with 2 vertical asymptotes, one without a vertical asymptote, and then the idea of getting holes in your graph as opposed to vertical asymptotes. So that's about it for rational functions. Hopefully you're practicing and getting better at graphing these.